present to you an article entitled Computational Resource and Cost Prediction Service for Scientific Workflows in Federated Clouds. This article was published in the Future Generation Computer Systems Journal from Elsevier, and it's available online since 27th of July last year. This is the resulting work of Michel and my colleagues Maristela and Aletheia. Aletheia was the master supervisor of Michel, and I worked in this article doing investigation, writing, reviewing, and editing this article. Well, the agenda of the presentation includes an introduction, related work. I'm going to present the CRCP's description, the workflow cases, and conclusion. Well, just to introduce contextualize the work, the use of cloud platforms has been widely encouraged in applications that required a lot of processing power and storage, like scientific workflows. Cloud federation platforms allow interconnection and interoperable cloud providers with resource management through an unique interface. So cloud federation platforms allied with the efficient necessary to execute scientific workflows is the challenge. And we pose the research question in the sense of discovering or investigating the possibility to automate a federated cloud platform service to efficiently select computational resources according to user needs for scientific workflow execution. Computational resource and cost prediction service, what I'm going to call CRCPs, used greedy randomized adaptive search procedures, grasp heuristic, and multiple linear regression method to predict user resources. For the prediction function, we predicted time execution and cost of each workflow. Historical database was built by monitoring executions of the workflows. We did a related work study based on these 6 works listed here. The first one is Coutinho, Drummond, Frota, Oliveira. The title is Optimizing Virtual Machine Allocation for Parallel Scientific Workflows in Federated Clouds. It was also published in Future Generation Computer Systems in 2015. They also used federated clouds, used grasp heuristic, but they did not use cost and time allowance by users' preference, and it was not transparent to users. The second work is Abid et al., 2018. It was published in the Journal of Supercomputing. They worked with cost minimization for bag of tasks workflows, also in federated clouds. They also used GRASP, but did not focus on cost and time transparent to users. Zhou et al. In 2019 published the article entitled Cost and Make Span-Aware Workflow Scheduling in Hybrid Clouds. It was published in the Journal of Systems and Architecture in 2019. They used hybrid clouds, and the technique was genetic algorithms, and they did not focus on cost and time and transparent to the users. Abel Serum et al. In 2020, they published the article entitled Self-Adapting Cloud Service Orchestration for Fulfilling Intensive Sensor Data-Driven IoT Workflows. They also published in the Future Generation Computer Systems in 2020. Sorry. They used ARIMA technique, and they did not focus on cost and time and transparent to users. Genese et al. In 2020 published the work entitled Time Discretization for Speeding Up Scheduling of Deadline-Constrained Workflows in Clouds, published in the Future Generation Computer Systems in 2020. And they used a hybrid clouds, not federated clouds, and ILP, and did not focus on cost and time and transparent. Fan et al. In 2020 published an article entitled Predicting Workflow Task Execution Time in the Cloud Using a Two-Stage Machine Learning Approach in the Transactions and Cloud Computing 2020. They used hybrid clouds and machine learning techniques, but did not focus on time and cost, and it was not transparent to users. So our proposal, the CRCPs, used in federated clouds, use grasp and multilinear regression, focus on cost and time, allowing users to choose, and it's transparent to users. So the CRCP's description is that it's a service to assist workflow users in appropriate choice of resource to be allocated in cloud platforms. Users' choices are high performance and low budget executions. Parameters prioritized according to the workflow needs. And federated cloud characteristics considered various types of virtual machines offered by providers, maximum number of virtual machines that can be allocated by specific providers, cost of communication between resources of different clouds, cost of data transmission from storage and download upload. Number of variables is big and several possibilities can be arranged to resource estimation. So we decided to use GRASP metaheuristic to resource allocation and associated with multiple linear regression method to optimize resource choice. CRCPs allows user-defined resource allocation most adequate criteria to work with different workflows, more efficient versus cheaper execution, or the balance between efficiency and cost. The multiple linear regression method estimates execution time and cost among software items in the workflow, and we used 20 variables related to these software executions, which were empirically selected, like time, software runtime in seconds, CPU usage by user processes, systems, CPU usage by system processes, IDL CPU, wait and waiting processes, used memory, buffer, using buffer, cache usage, free memory, disk read operations, disk write operations, byte send over the network, running processes, blocked processes, new processes, software that compose the workflow, and the number of reads from a file, number of CPUs, size in megabytes of the software input file. So after defining all those 20 variables, we also defined the number of variables that compose the regression equation using the stepwise method. The stepwise method is an iterative one that builds regression models by adding and removing variables at each stage, using a criterion expressed in terms of a partial f-test, the f to enter, or a critical significance level to enter. It forms by comparing a model with its submodel. So the variables established by the stepwise procedure are time to be estimated, key and T reads, number of reads from a file, factor core, number of CPUs, and program software containing in the workflow. The multiple linear regression data set experiment design is composed by two bioinformatic workflows defined according to their tracking data. And if programs were not previously executed by CRCPs, we handily selected 180 simulated runs for training base from Bounty, Top Hat, Trinity, and Blast softwares that are very common in bioinformatics area. And then we did 120 actual observations of Bounty executions to be used as training base, and 120 observations of actual executions added for Top Hat, Trinity, and Blast softwares. It was possible to evaluate the predicted model performance as Bounty was not known from real executions of Top Hat, Trinity, and Blast. Multiple linear regression equation was obtained where time is the dependent or prediction variable, quantity of hits, factor call, and program are independent or variable predictors in this time equation of multiple regression. The beta 1 to 3 regression coefficients and beta 0 constant are determined so the sum of squares is minimal as indicated in this equation. The grasp heuristic used to predict the dimensioning of resource in the proposed survey assumes that P is a set of virtual machines from a provided J. Users' requirements include maximum financial cost, CM, maximum execution time, TM, workflow includes disk storage capacity, D, memory capacity, M, processing power, NC. Each type of virtual machine that has specific financial cost, CP, of allocation per period of time that can vary from a minimum time to 1 hour, has disk storage DP, memory capacity MP, number of cores NP, cost of upload UCP and download DCP of virtual machines, cost of storage transmitted data CDP. Maximum limit of virtual machines and age that can be allocated by users, varying by cloud providers. The cost function F minimize financial cost and total execution time, where alpha 1 and alpha 2 are variables estimated by users' criterion of best cost or less time. And penalties are coefficients for violation of time and cost requirements, as the equation shows here. So the workflow that we use are two different ones. The Schizocaromyces spongifungi from the RNA-seq experiment data. It's composed by this workflow. The legend has different colors. The input data here inputted in the Top Hat software, and we have the mapping from these files to Booty and to Top Hat, and then the data are assembled to Trinity, and they are computed by Blast using the UniProst database to compose the result of the workflow. And the second workflow is the Aspergillus fumigatus fungus, the RNA-seq experiment data. It has also input data to Top Hat and Bounty other data input set. And then they have the Trinity that are inputted into Blasta software using the UniProst data set, database to generate the output of the workflow. The experimental setup includes two different scenarios. The first scenario where the workflow program's information already exists in the historical database, and there's no need to obtain information from simulated executions. And the second scenario, when the information is not included in historical database, so it's necessary to instantiate the simulated executions to fill the database with program information from small executions using synthetic data, which will help to the accuracy of the estimations. Workflows executions were distributed in 3 different virtual machines from Google provider. Executions were replicable 20 times with a total of 60 observations from each CPU, varying from 2, 4, and 8 CPUs, memory with 7 gigabytes in each, and hard drive with 60 gigabytes in each, and operating systems Ubuntu 14.0464. The multiple linear regression results include the variance inflation factor, VIF, indicating absence of correlation between variables, as it shows values less than 5 here. And the evaluation indexes validate and verify accuracy of multiple linear regression forecast model, evaluated by BICE, mean absolute error, root mean square error, mean absolute percentage error, and the R square between 0 and 1. So the results show very good results of prediction using multiple linear regression model. For the GRASP results, we implemented executions in the BioNimbus Z, which is a federated cloud platform, as it's illustrated in this diagram. It uses the Zookeeper to align the database with different jobs and Java server faces to input the workflows. We used Google Cloud Platform and Amazon Web Service using only dedicated instances of virtual machines. The instance used in the CRCP's experiments are 16. The instances are declared here, the cores here with CPU cores, and the memory here. The results in the execution of CRCPs demonstrated by the blue line, the estimated time, and the orange line, the real time, shows a very good performance in all 16 different instances of the federated cloud, showing that the time and showing that CRCPs can do very good job with federated clouds in the workflows. As a conclusion, we presented the CRCP's provisioning service for scientific workflows in federated clouds. The CRCPs merges GRASP metrics to multiple linear regression to predict resources. This service provides workflow executions in a flexible, dynamic, and transparent way to users. The CRCPs allow users to choose high performance, low budget, and set execution limits for the workflows. And two bioinformatic workflows validated the CRCPs using BioNimbus Federated Cloud Platform. We thank you very much for your attention, and questions could be sent to myself in my email, which is gedini@unb.br. Thank you very much for your attention. I'm very pleased to present this article.